So this video is for AP Bio, topic 8.3 and 8.4, talking primarily about population growth patterns such as exponential growth and logistic growth. Okay, so let's go ahead and first start off with an example, of bacteria. So bacteria reproduce very quickly. So they reproduce by binary fission. It's a type of asexual reproduction where one bacterium can become two. It'll divide asexually, make a clone of itself in about 20 minutes. And then now these two are going to become four. And then these four reproduce, and now there's 8. And then the 8 reproduce, and now there's 16. 16 becomes 32. 32 becomes 64, etc. So this is a very rapid growth, where in exponential growth, this is exponential growth, you're going to end up seeing, as you count the population. So what we just saw went from 1 to 2 to 4 to 8 to 16, 32, 64. It's going to keep on doubling, 128, 256, 512, and it's going to go through exponential rate of growth. And in exponential growth, the population grows as if there's unlimited resources. Now, in bacteria, they could be growing exponentially within a petri dish until they run out of space or run out of nutrients. But in reality, a population, you don't see exponential growth sustained for very long in nature. But let's still spend some time talking about it. So when we talk about exponential growth, the per capita or per individual growth rate stays the same. So in the bacteria, it was doubling, right? Every 20 minutes, that rate of increase stayed the same. And therefore, as the population got larger, it grew. There's even more now doubling, and then all of those doubled. And so as the population gets larger, it grows faster and faster and faster. So humans have been experiencing exponential growth for a while now, and our population is increasing like crazy. All right. Now, when we talk about exponential growth, it ends up making what we call a J-shaped curve. And you may come across a couple different styles of math problems are getting asked about population growth. So in this one, we're going to just look at how do you calculate the growth rate of this population in a given time period. So in this, we're specifying between day 8 and day 14. So really, you're going to find what is your final population. Here it was 150, and your initial population is 50. And now what we're going to do is we're going to find the final minus the initial over or divided by the change in time. And so here we find that the average rate of growth was 17 individuals per day was added to this population. And so if you ever have to calculate or find the rate of growth from a graph, you're going to want to find final population size for whatever time frame they've mentioned minus the initial divided by the change in time. Okay, good. Now, something else you're probably going to see when talking about population growth rates is this value called R. Now, R stands for rate of growth. And there's different ways to phrase it, but basically R is growth rate. And out of these two populations, we can look at the slope of the line, and we can envision that the red line is this red population is growing at a faster rate compared to the purple population. So if I were to assign R values to this, these are arbitrary. I made them up, but the red line would have a higher rate of growth compared to the purple line. So it's growing at a faster rate, and therefore it has a higher R. Okay. So let's go ahead, though, and talk about some of the formulas you may see from College Board. Now, when we look at these letters, a capital N stands for the population size, and capital B is birth rate, capital D is death rate. And so this is per capita or per individual in a population. And so just realistically, when we think about birth rate and death rate, if we have more births than deaths, our population is getting larger. If we have more deaths than births, our population is getting smaller. Now, this area that I've circled here is kind of it uses notations that you would use in a calculus class, but really that dn over dt is really talking about how is the population changing over time? Like, how is it growing? What is its growth rate? And so here, it's just words for what I just said, but if a population is increasing in size, you'll have a positive growth rate. If it's decreasing in size, you'll have a negative growth rate. Now let's go ahead though and look at the formula for exponential growth. So we see our max, that's the maximum per capita growth rate of a population. So that's per capita, just means like per individual. And so here, if a population of lemurs has an R max of 0.25 per year, now that 0.25 already takes into account the births and the deaths. Like this is our overall average rate of increase for this population. So it has a R max of 0.25 and a population of 327 individuals. What will be the new population size after 1 year? Okay, so we take our formula and our R max is 0.25 and N is our population size. And we find that the change in the 1 year, like it was only 1 year, so our denominator is a 1. So really like our change in our population as it basically increased by 82 individuals. So in that year, there were births and there were deaths, but we had a surplus or an additional 82 individuals by the end of the year. So I'm going to take my 327 original population size, and I'm going to add 82 individuals. So now the new population size after 1 year is 409. Now, realistically though, populations cannot grow exponentially forever. There is going to be limited resources. Like you can think of Earth as like an island. There's only so much land. There's only so many nutrients. Like if you think about like the law of conservation of matter, and like there's a limited or finite amount of resources on Earth. And so us humans, populations, like as we, as humans especially, undergo exponential growth, there's going to be a point where we're running out of food, of space, of water. And then what's going to happen? Now, some would argue that's already happening in some parts of our world. Okay, so let's go ahead though and first talk about population density so we can understand what happens as a population density increases. So here I have a forest. Let me move my face. And if I apply a grid to this forest, I can kind of measure like the population density in a specific area. So in this grid though, because these trees are in a random dispersal pattern, it's not super like even throughout the population, but like in this bottom left grid or quadrant, we would find 9 trees per hectare. So that would have the highest density out of these 3 options. Now, when we talk though about populations, as their density changes, so like how many individuals are in a given area determines its density. So for example, I teach in California and my average class size is about 40 to 42 students. Now that would be a 40 students in one classroom is a high population density compared to another classroom that may have only 20 students. That would have a lower population density. And as density changes, it has an impact on competition for food and resources. So we can totally picture this, that as you increase the individuals within a population, if they're all still in that same area interacting together, they're going to have a more intense competition. It's going to get harder and harder to get all of the things necessary for life: shelter, water, food, I was going to say comfort. That's not one, but space, right? So that is, as your population increases, it gets more and more difficult to have access to all of the requirements for life. And so we cannot grow exponentially forever. If you think about this forest, if every seed that was ever dropped sprouted and grew to a mature tree, there would be intense competition for root space, for sunlight, for water, for nutrients. This forest tree population could not go on increasing at a constant rate forever. There's just too many individuals, and as this population density increases, each individual has access to fewer resources. Okay, so if we think about what happens as populations grow and grow and grow, you're going to get way more intense competition between individuals of the same population. And that's going to lead to natural selection as well. But you also have predators. As your population increases, it makes it easier for predators to find you. And then you have abiotic factors that can influence a population size. So you have things like available water, or are there enough nutrients in the soil, or is there enough sunlight to produce enough food to support the food web or the population in that area. So you have both biotic and abiotic factors influencing how large a population can grow. So, oops, darn, okay. So when we talk about this, these factors that limit how big a population can grow are called limiting factors. So let's say we have a population of elephants here. And there's reasons why these elephant population would not grow exponentially. So it could be nutrient availability in the food that they eat, the amount of energy, how much food is actually growing in their area because they're herbivores. Is there enough plants to give enough calories to support the whole population? Shelter, water, refuge from predators, all of these things are factors that limit how big a population can grow. And if a population starts to multiply, they have births, the population increases in size, these limiting factors limit how big a population can increase. And so you're going to have births, but you're also going to have deaths. And so how those balance out really impact the population growth. And so if we look at, there's an area on a graph though. So here, a population may undergo exponential growth. Sorry, I had to hit pause. I think I was saying as a population undergoes exponential growth, it starts to feel the effects of what we call density dependent limiting factors. So maybe low food supply, more intense competition, limited space. And so therefore the population reaches its maximum capacity for an area. So we call that the carrying capacity. The carrying capacity is like the max number of individuals that an environment can support of a particular population. And so let's go ahead and, So as a population approaches carrying capacity though, the growth rate slows. And I'll talk about that and show a couple examples in a bit. So let's go ahead though, okay, and see some of these limiting factors that exist in nature. So we have two populations here, and you can see that population A has a lower population density and B has a higher population density. So when we think about food availability or like energy availability, we want to ask ourselves which population is going to feel the effects of a limited food supply. It's going to be population B, right? So population B is going to have pretty intense competition for resources. Competition is a limiting factor. It's going to limit who's able to survive and based on the amount of food that they were able to access. Now, which population is more likely to have disease spread? That's also going to be population B. Think about like with COVID, for example, we had the social distancing, the spacing of 6 feet. Like the more spread out we are, the less likely the disease will spread. Same thing in populations. Diseases spread through natural populations in the wild. So the higher your population density, the easier disease will spread and limit how big your population can grow. So disease is really going to have a greater impact the greater the density of the population. And then when we talk about predators and which population is going to feel the effect of predators, it's really going to be population B. There's going to be more prey available for the predators. So here, now if there's like a tsunami though or something, does density really matter on how the populations are impacted? Not really. Natural disasters don't really have anything to do with the density of a population. They're just a fluke thing, unfortunate thing that happens, and it will affect both. Same with pollution. Pollution in an environment, whether it's air, water, noise, light pollution, they're going to impact populations regardless of the population density. So when we look at limiting factors, we can divide them into two categories. Here we have limiting factors that are density independent. They're going to have an impact on the population size regardless of the population density. And then we have ones that are density dependent. So that would be your competition, your predators, your disease. Those are all limiting factors that large, dense populations are more strongly affected by compared to small, less crowded populations. So limiting factors really limit how big a population can grow. And they're divided into two categories, density independent and density dependent. Okay, so let's go ahead though and go back to logistic growth and talk about, there's the words behind it. So your density independent, okay, predation, disease, competition, okay. So let's go ahead though and talk about this graph. So when we talk about a real life example of logistic growth, so the elephants in a certain region in Africa were hunted to almost extinction in the 1960s, for their ivory tusks. And so some rules were put into place to stop poaching. And what they found was that the population underwent exponential growth as they recovered over the decades. So it was as if there were unlimited resources. But eventually their population density increased to a very high amount, and now there's less resources per individual, which led to more intense competition, which led to not all individuals surviving, and now you have some deaths. But the survivors are going to reproduce, and so then you have births, and then if you're above carrying capacity, you're going to have deaths, and you find the population is going to fluctuate around the carrying capacity. And so this area here is usually, if you're ever asked to find the carrying capacity, kind of find like the average. If you see it like wiggle a little bit, okay. So the carrying capacity, when you talk about species on Earth, we can divide them into like K-selected species or R-selected species, which I'll have a whole different video on just that topic. Our K-selected species are going to be found living in populations that are pretty much always at or near carrying capacity. And then your R-selected species are going to grow so rapidly that it's like they're experiencing exponential growth, even if it's not forever. Okay. So when we talk about logistic growth, though, the per capita growth rate gets smaller as the population approaches carrying capacity. So let's go ahead and talk about how mathematically we can look at logistic growth. So here I have a graph of population over time. Now initially, so let's pretend that there was a forest fire. And so the forest was cleared and now we have this open soil. And new seeds land on the soil and then rain happens and it starts to germinate and they're like, ooh, this is like unlimited resources. Ooh, they start to grow. And so you start to have a growth rate begins to increase. And then right at this purple area, there's like a high growth rate. This population is like thriving in this open forest because it was like there was unlimited space, unlimited sunshine, it's raining, there's unlimited water, and growth is good. So if I compare this orange to this purple region, R, the rate of growth is going to be higher in that purple area. It's a very pretty like steep rate of growth. However, as the plants begin to take hold within that forest, now any new seedlings that start to germinate, there's already existing plants. So competition for space is going to become intense and the growth rate is going to slow. As the population density increases, the population begins to feel the effects of those density-dependent limiting factors, and your rate of growth is going to decrease. Now, eventually, you get to a point, possibly, where the population birth rate and death rate are equal. And so this, at carrying capacity, the rate of growth is 0. The population is stable. So we can see as we go through logistic growth, the rate of growth is going to change as the population density also changes. And we take into account the amount of available resources, density-dependent limiting factors such as predators and disease, etc. Competition. So there is a formula, though, that goes with taking into account carrying capacity. So here, I like to think about this left-hand side as like how much will the population change in a given amount of time. So we have our R max still, but we also now take into account, there is a carrying capacity. It's going to get intense. As the population gets closer and closer to that carrying capacity, it's going to be harder and harder to survive. And that's why we include K in this formula. So let's go ahead and see just one example. So if we have a bird population of 170 in a forest, and the forest has a maximum annual rate of increase of 0.6. So that's our R value. If the carrying capacity of the forest is 800 for this species, what is the expected population size after 1 year? Okay, so here we have our max, our rate of increase is 0.6. Now our existing right now population is 170. And then in the brackets we see, well, what will happen as the population is increasing at 0.6 R, as it gets larger and larger and gets closer to 800, there is going to be more intense competition. They're not all going to survive. So we include that carrying capacity, that K, as part of it. So here, as we continue, oops, my face is in the way, I find that the population is going to increase by 80.3. And we're just going to round up because it's individuals, right? So here we start with our initial 170 plus our 81 that we added to our population. And we find that our new population, N, is 251. All right. So to summarize the two types of growth, this is my last slide. Good job for hanging in there. We have exponential growth and we have logistic growth. And really the difference is, that in exponential growth, the larger the population gets, the faster it grows, versus in logistic growth, the larger the population gets, the slower it grows. That R value begins to decrease because the population is at or near carrying capacity, and it becomes very difficult to have a lot more births than deaths. They begin to equalize, and now you have no growth. All right. I hope this was helpful, and great job.